This webcast continues the discussion of the lab on conservation of momentum. Now we are beginning part 3, where we're looking at inelastic collisions. This part 3 uses the same University of Colorado simulation that we were using for part 2. There's only one difference. So as you set it up, click in velocity, kinetic energy, values, constant size, and more data. But this is very important. Very important. You must change the elasticity from 100% to 0%. Because in this portion of the lab, we want to look at completely inelastic collisions. Okay? But the basic process for getting data is similar. You will go to tab 3, the third tab in the Excel template where it says Data Part 3 Inelastic, and we're going to do the same thing that we did for Part 2. We're going to change the masses of those two spheres, and then after we have them go through an inelastic collision, we're going to record the final velocities. So for the first row, I'll set both of these to a mass of 0.5 kilograms. I do not touch the initial velocities, leave those at the default values. Okay, the only thing I'm changing is the mass to change them to the values here in the table. And then I click the play, let them collide. Ooh, they've stuck together. Okay, and they're both going to the right. And I see that both of them have a velocity, a positive velocity of 0.25 after the collision. Okay, so I fill that into my table. Okay, and I'm going to keep letting it run until they have gone out of the box. Then I can return the balls so that the only thing I'll have to do is to start again with different masses. Okay, so you should fill in all of this table with your data. After you've gotten the data, you will paste it here at step 44. And so I'm just going to paste a copy of my data table. Okay, and then we want to make a scatter graph of the system momentum after the collision versus the system momentum before the collision. Okay, so I'll go to the Excel file. This did not create it automatically for me, but that's okay. So my independent variable, the one I want on the x-axis, is going to be the, system momentum after the collision versus system momentum before the collision. So this is going to be the system momentum before the collision. That's in kilogram meters per second. And then the dependent variable will be the system momentum after the collision, also in kilogram meters per second. Okay, so now I have my tables set up, and so I'm going to I want to copy the system momentum before the collision, so I'm going to go to that part of the table. Now these values, these cells have formulas in them, and if I paste the formula, I will get something that's garbage. So I want to copy these cells, but when I come over here to paste them, I only want to paste the values. So go to the drop-down list under paste and only paste the values. That way it's just numbers, it is not the formulas. And then I'm going to do the same thing to copy the system momentum after the collision, but I don't want to paste those formulas. I'm going to go to paste and only paste the values. Okay. And so let's get this graph. I'm going to just do a scatter plot here. So I'll insert my scatter plot, and looks good. I can see that it's nice and linear. I have, because my origin is in the middle of the graph, the labels on my Y and X axis are kind of interfering with me reading the graph. So I'm just going to change the position where those are written. I'm going to format the axis and put them at a low position. That way they are not interfering with me reading the graph. There we go. Okay. So on the x-axis, this is the system momentum before the collision. That's in kilogram meter per second. The y-axis, this is the system momentum after the collision, also in kilogram meter per second. And my chart title is System Momentum After the Collision versus the System Momentum Before the Collision. Okay, so I have a nice linear graph. It goes through the origin here. And so let me copy this and put it in my report. This is at step 45. This is figure 6. Okay, and so now we want to talk about the relationship that we see here. I mean, it's linear, it passes through the origin, and so, we can say that. So the graph in figure 6 is linear and passes through the origin, which means that the linear momentum after the collision is directly proportional to the linear momentum before the inelastic collision. Okay, so we've identified the type of relationship. Let's get a slope so that we can write a physics equation. So I'm just going to do a linear analysis, linear regression. I'll delete this data that we had from the previous one. Okay, so I need to give it my y values, which is the momentum after the collision, and then the x values, the momentum before the collision. Here we go. I'll just make sure that all the columns are wide enough for the data that's contained in them. This looks like a very nice fit, and I'm getting a slope here of 1.005. Okay, so this is the linear regression for part 3 inelastic collisions. Okay, and so I'll just copy this linear regression because this is the evidence that shows how we found the slope here. And so now we can write the slope is, well, I remember the number is 1.005. Let me go look at the graph to make sure that I know the units. Oh, I had the same units on the y-axis and the x-axis, and so this slope is dimensionless, right? The kilogram meters per second canceled when I calculated the slope. Okay, so my slope is dimensionless. The meaning of this slope, okay, so again, if we look at that graph, it's saying that as the system momentum before the collision increases, the system momentum after the collision also increases. So let's see here. So for every additional 1 kilogram meter per second of system momentum before the inelastic collision, the system momentum after the inelastic collision increases by 1.005, and that's kilogram meters per second. Okay, so as the momentum before the collision increases, so does the momentum after the collision. And so if I wrote a physics equation, I'd say that the momentum after the collision equals 1.005 times the momentum before the collision. They're essentially the same, right? This slope is very close to 1, so the slope is essentially 1, which means that the system momentum is the same both before and after the inelastic collision. Therefore, the system's linear momentum is conserved during inelastic collisions. Okay. Then the last question here is, you calculated the kinetic energy of the system both before and after the collision. Well, you know our spreadsheet calculated it. Let's just go look. Okay, so here's the final kinetic energy, and there's the initial system kinetic energy. Ooh, they're not the same. Look, I have 0.3125 joules before, and I only have 0.03125 joules after. That's in the first row. 0.4375 before the collision, and only 0.0169 after. In every case, as I look through these rows, the final kinetic energy after the collision is smaller, much smaller really, than the kinetic energy before the collision. So during the inelastic collisions, kinetic energy is not conserved. It is not the same. So let's say that. The table at step 44, that's where our table of data was. Shows that the kinetic energy of the system after the inelastic collision was always smaller than the kinetic energy of the system before the collision. Okay, and I said always because that was in every case. So therefore, the inelastic collision resulted in some of the kinetic energy redistributing to other energy storage modes. You know, during the collision. It could be that some energy was dissipated. It could be that, you know, in some collisions the height of one of the objects gets increased. It rolls up on top of the other. But anyway, some of that kinetic energy, we know it's not being destroyed because energy is conserved, but it is not remaining stored as kinetic energy in the system. Okay, so that